Okay, this is my video for the open-ended questions of test 3. The first question about the puck that's 100 grams revolving around a circle with a 20 centimeter radius, and what the RPMs would be if the radius were 12 centimeters instead of 20. So I first looked at the tension equation, which is just the T equals mass times velocity squared over radius. And using that, went on to use the initial tension in that string of the mass times the radial velocity times the radial velocity squared times the radius. So that's the initial equation, and I set that equal to the equation, what it would be after the radius was decreased to 12 centimeters. So yeah, mass times radial velocity squared times radius equals mass times the second radial velocity squared times the new radius, which is 12 centimeters. So from there, just solving for the radial velocity of the 12 centimeter circle from those equations, since those were set equal to each other, just solving it for that comes to the square root of the first radius divided by the second radius, all times the initial radial velocity. So I'll just plug that into my calculator here. So square root of that initial 20 centimeter radius divided by the new 12 centimeter radius times 120. So it comes out to about 154.9, which I would probably just round to 155 rotations per minute. So that just gives us that second radial velocity. So 155 rotations per minute is the answer I got on that one. The second question asks about the quadriceps, muscles in the leg. It gives you the values of T and C and the force, and finding that when the leg is at a certain position. So the problem gives us when T, the tendon's at an angle of 25 degrees with the tibia, assuming that C's 30 newtons, the force is 12.5 newtons, and the leg is extended at a 40-degree angle. So using that information, as it says, theta is equal to 40 degrees. And just looking at the diagram, the weight has a 0 torque, and that T that's going up, that's pointing upwards on that diagram at the bottom, also has a non-zero torque. That's what I meant to say. And the force, they have non-zero torques. So using that, I just, for the torque, for the T, I guess, since it has that angle of 25 degrees, just set that equal to T times sine 25 degrees. The weight to the sine 40 degrees, and force is also 40 degrees. So F sine 40 degrees. And okay, so solving that one, the help that I found, which was really helpful. Using the second condition of equilibrium, that equation, I guess, is having me basically just subtract those from each other. So the t sine of 25 degrees times d over 5 minus 13.4 newtons, which was taken from that weight. So the W sine 40 degrees is converted to the 13.4 newtons minus the 8.4 newtons of the weight of that force. So the force sine 40 degrees converted as the 8.4 newtons. And that's just set equal to 0. So having all that kind of jumbled up, I just solved for t. So solving for t, not too bad. So just gonna bring over that 15.1 newtons divided by the sine of 25 degrees, and that's all equal, and that's multiplied by 5. Yeah, so 5 times 15.1 newtons over the sine of 25 degrees. Let's see. Okay, so that gives me about 178.6 newtons ish. So that's the answer I'd put for that one, for that value t, when the tendon's at those certain angles. So I'm just going to go ahead with the 178.6 or 179 rounded up newtons for that value. And then the last one, the question about the Jeep. This took me a really long time. So, okay, so starting off, I just used, I found some help that led me to, what is this called? Just the final velocity equation. The velocity squared minus m squared. And just set that equal to 2 times the mass of the curve, times gravity times times the seconds, the time. So yeah, so v squared minus v squared equals 2 times mass times gravity times seconds, and then using that solve for v. So solving for v, bring that over to the other side, the 0 squared just cancels out. G times S. So before plugging in those values, it's velocity will equal the square root of 2 times mass times gravity times seconds. And then with those values inputted, it'll be 2 times 0.7 times gravity times 9.8 times 0.630. So that gives us that initial velocity of 2 times, oops. About 2.94 meters per second, that initial. And then moving on to the energy, needing that total energy. So the equation that I used for that is the energy equals half the mass of the car times the velocity of the car squared. So that's the energy before the collision. And then also using the equation for after the collision. So the kinetic energy of after the collision, similar, but 1/2 times the mass of the car plus the mass of that and the mass of the Jeep times the velocity squared. And that second part should give us the combined mass of the system. And then comparing that to the potential energy of the system here, potential energy of that second, the mass of the Jeep plus gravity plus the height that the Jeep was off the ground, which is the 1/2 meter. So using those two equations, we can find the total energy, which is the kinetic energy plus the potential energy. So adding all that up from those values from before, 1510 plus 1815. Plus 1815 plus 2040 equals 12.5 plus that initial velocity squared, the 2.94. 2.94 squared. We'll also add the mass. Oh, I should say that's where I was getting those numbers. The mass of the Jeeps, the 1,815 kilograms plus gravity. Or I guess not plus, I'm sorry, times. Plus that 1/2 meter that the Jeep was raised. And then if we set those values equal to each other, we'll find the equation to be 1/2 times the mass of the car times the velocity of the car squared equals that number 32,079.97, and then we'll solve that for the velocity of the car. So if we solve that equation for the velocity of the car, okay, so that'll be the square root of 32,079.97 divided by 10, 1510 was the mass of the car in kilograms. And that will give us, that'll give us the initial speed. So it's 6.518, so about 6.52-ish meters per second. And in miles per hour, miles per hour would be about 15.4 miles per hour. Okay, all done. Thanks.